In this lesson, we're going to take a look at one of the trends that the periodic table shows us, a periodic trend, and that's the trend in atomic radii size. Now, before we do that, let's talk a little bit about some terminology. The nucleus is the singular form of the center of the atom, right? That's where the protons and neutrons are. If we're talking about more than one nucleus, then we're talking about nuclei. That's the plural. Radius is, of course, the distance from the center of a circle to the edge of the circle. If I'm talking about more than one radius, then I'm talking about the radii. So don't get the singular and the plural goofed up here. Now, atomic radius is hard to actually measure because the atom is fuzzy, right? We have the Heisenberg uncertainty principle that tells us we can't know both the momentum and position of an electron. The orbitals are probabilities, right? That's regions of space where electrons are likely to be found. So the actual edge of an atom is hard to define. So instead, what we do is we define it as half the distance between the nuclei of two identically bonded atoms. So half the distance between these two nuclei. Now, like I said, we do this like this because electrons are fuzzy, because single atoms are pretty rare. Only the noble gases really exist as single atoms. Everything else is bonded. And because otherwise it's hard to define. Now, as we move across the periodic table, we're going to see a trend, and as we move down the periodic table, we're going to see a trend. Now think about this for a minute. What happens to the number of protons as we move across the periodic table? Right? Well, we go from hydrogen to helium. The number of protons goes from 1 to 2. We go from lithium to beryllium to carbon, nitrogen, oxygen, fluorine, neon, right? Every time we move right one step on the periodic table, we actually add one proton. Every time we move down on the periodic table, we do go from, say, helium to lithium. We've added a proton, but we've also gone from row 1 to row 2. That is, we've gone from the first shell to the second shell. We've added another shell of electrons to the atom. So if we think about this, then this table makes a lot of sense. Here's hydrogen over here. It's actually got an atomic radius of 53. This is in picometers. Helium, you can see visually, is actually smaller. It's only got an atomic radius of 31. Helium has got 4 times as many particles in the nucleus, right? Hydrogen's 1 proton, helium's 2 protons and 2 neutrons. Helium has twice as many electrons, but because that pull from the protons is stronger, because there's twice as many protons, the electrons are actually pulled closer to the nucleus. So moving from left to right, we see this trend where the atom is actually getting smaller as we go from left to right, and that's because we keep throwing more protons into the nucleus of the atom, which creates a stronger positive charge, which creates a stronger pull or force of attraction between the nucleus and the electrons. So it does totally make sense that as we move from left to right within a row, within a period, that the atoms get smaller. But notice what happens as I move down a column. Hydrogen to lithium, that's a huge change, right? Why did the atom get so much bigger when we went down one step? Shouldn't have got smaller again since we added another proton to go from neon to sodium? Well, we did add a proton, but think about where that next electron went, right? This electron just filled in 2p6. This electron just went to 3s1. It's not even on the same shell. It's now on the third shell, and the third shell is farther from the nucleus, so the atom got bigger, right? So moving down, we're adding electrons to the next shell. Moving right, we're adding electrons within the same shell, and the nuclear attraction, or the coulombic, I guess, because it's from electric charge, is stronger. And so this graph shows the calculated atomic radius of these different elements, and you can see the S block. Here's atomic number 1, hydrogen, helium. It gets smaller. Then we get up into the second shell, and then within the second shell, they continue to get smaller. And then we get into the third shell, and they continue to get smaller. And then we get into the fourth shell, and then it continues to get smaller. And then you have the D block in here, and the D block still follows that. And then the P is where it gets smaller, and then they jump, right? So you can see every time we get a new shell on the periodic table, the atoms get bigger. And as we move across the row, or across the period, the atoms get smaller.